I've never seen that one.
U node equals U.
It's basically like it's pointing to Q, and then
Oh, yeah,
P is pointing to the node. I don't know.
Start again.
Should I move up?
The title I have on here is a little bit different, so I'll read the slide. The title of this talk is Staterra Nutrient Injection System, and when I read that, I thought somebody laying on the table with but it actually has to do with something entirely different. The sponsor is Staterra, and the industry mentor, Eric Brooks, here. Thank you to the faculty sponsor, Randy Kahn.
Thank you, Arnie. So, hello, this is the Staterra Nutrient Injection System team. And first of all, we'd all like to thank you for staying for this long to hear our presentation. My name is John Hume, and this is Matthew X, Natalia Harris, and Dr. Ali. And basically, I'm gonna walk through the outline of our presentation. So, first, I'm gonna go through team roles, and then basically explain what we did in like a very shallow sense. We're going to talk through the project background, kind of the history and how we came up with this project. We're going to do project purpose, which is like kind of the project overview, and then we're going to go through and talk through how we designed the RTG, the solar, HMI, battery. After that, we're going to show you guys our results and give future implementations of this project. So team roles. So first up, we're going to have Matthew Hicks come up and talk to us about the controller, what he did for that portion of the project. Natalia Harris was mainly doing software, like human machine interface, and then I worked on the power supply, and then Zachary Ali characterized the RTD sensors. So the project that Staterra and we came up with was actually a separate project than that of those that were recommended by Arnie. We found our own industry sponsor, Eric Brooks, who also happens to be the president of Staterra, and with Eric's guidance, we had this project to fruition. So over here we see a couple of pictures of lakes in California. This is Lake Olson in Sacramento. This is Lake Ogo. You can see from the time base 2011 to 2014 on both of these that there has been a significant drop in water in both of these lakes. And this is because that there's been a severe drought in California. You probably all know this, but as of March 3rd, 2015, California actually entered their 4th year in drought. So it's like a week ago today. What is not common knowledge to everyone here is that California is almost solely responsible for about 65 to 70% of our nation's fruits and vegetables. So this put us in like quite a dilemma because we need the crops in California to grow, obviously, but we don't have the resources to keep dumping more and more water into the fields. So we have to find a better way to effectively deliver energy to the crops so that they can grow. And this is kind of like where Staterra comes in. Staterra and Eric basically had a vision to create a nutrient metering system that would give growers the tools to bring about higher crop yields. Our project was to create a system that would enhance existing irrigation networks in Salinas Valley, California, and it would do so by continuously and accurately delivering important nutrients in very low concentrations to soil-borne organisms. This would be in response to the irrigation systems that were already in place turning on. Then our system would automatically record the process metrics and then continuously log them for later retrieval. Next, we have Matt who's going to go through the project overview and talk through this section of the project.
So here's an overview of the system. There's an irrigation system in the farm. There's an injection module that will detect the flow of when the irrigation system comes on, and that signal will be sent through a CAN bus to the system controller that will activate the nutrient injection pump and inject the nutrient into the irrigation system. It's all powered by a primary power module and solar charger, and it can be accessed by human-to-machine interface through the system controller via Bluetooth, and to get the data log file and change system parameters. So I was tasked with picking out a controller. The high-level goal of the controller was to be responsible for processing data from and control various modules within the system. It had to have a programmable data logging interval that recorded system information into a data file. And it had to be able to communicate with an Android device, provide user real-time status, system status, and allow the user to configure certain controller variables and retrieve the data log file. Additional constraints were that it had to be low power consumption. It had to withstand harsh outdoor conditions, therefore having operating within an industrial temperature operating range. It could not exceed $100. The code developed for the microcontroller had to be portable for future custom controller design. It had to have certain capabilities to communicate with other devices such as SPI, UART, ADC, SD cards, and some sort of wireless communication. It had to be easy to use. Had to have low-cost development tools, strong community support, and the board had to be readily available, continually developed on. So we considered 3 different platforms: a single-board computer running an operating system such as Linux or Android, or microcontroller development platforms with an RTOS or a custom operating system. And we considered the complexity of these devices, the costs, the power consumption, the technological risks of developing on these platforms, the development tools and the community supporting them. And we ended up going with a microcontroller development board with a custom operating system. We considered many different ones, even within that realm, but we decided to go with the LMX Xeno, which was used for the proof of concept. It's a 32-bit ARM core microcontroller operating at 72 megahertz with a fairly large size of flash memory for user program space. Has 3 UARTs broken out, SPI, a CAN interface, a real-time clock built into the microcontroller, and a micro SD slot on the back for the data logging. It also has I don't know how to use the pointer. It has an external connector there for modules, such as like a Bluetooth or Wi-Fi. So when we developed on it, it's an Arduino clone. So it's programmed using a similar platform called Maple in C and C++. We programmed the Bluetooth module with a speed up to 1 megabit per second that transmits the data file over UART and receives HMI commands for configuration and to get system status. We also initialize a 32-bit timer for the logging interval to log data to a file, and we utilize the RTC and SD library for real-time clock, time stamping, and recording the data to a file. In conclusion, it was a great proof of concept. It demonstrated data logging, HMI communication, interop between process sensors, but it's really not something that you would want to release as a consumer product. So we explored other options for the future, and we decided to implement a PIC microchip, 32-bit microcontroller, and a custom board. We had an opportunity to test the development platform, which is Microchip's new MPLab Harmony, which makes it easy to implement a lot of the peripheral features of a microcontroller, like Wi-Fi or CAN and UART. And we did that when we brought up the CAN bus using 2 starter kits that Microchip makes. And we decided to go, we considered RS-422 and 485, but we decided to go with CAN because of its deterministic communication protocol for multiple devices, and it's specifically designed for industrial applications. It also operates at a high speed, at long range with low errors, and it has low power during periods of inactivity. And I'll turn it over to Natalia to cover the HMI.
So the human-to-machine interface needed to be simple, easy to navigate, not too many buttons, not too complicated. We needed a wireless connection for data transfer, download files from the microcontroller. And we needed to be able to walk up and read live system updates, like temperatures and movement levels. And we needed a design platform that was a moderate learning curve so that later on, for the future of this project, people could add on to it. And so for our wireless connection, we knew we wanted either Bluetooth or Wi-Fi, something already established. And we ended downfall of Bluetooth was that it had a slower bit rate. So for the future of this project, we would recommend Wi-Fi. Even though it's a higher cost, it will be much faster for a guard to go out there and pull much more amounts of data from the system. And so the platform decision between Android and iOS was Android. And Android runs with Java and XML files, and the development platform was much easier to use. It had excellent configuration. And when you go with Android, the publication of the application is going to be much easier, whereas iOS, even though it's a little more popular, it's a hassle to publish. And what we're not trying to solve an application, we're trying to solve a system accompanied with it. And so I have this small demonstration to kind of step through that. So you have your Android screen, and you go into your settings. Make sure your Bluetooth is on. You would walk up and make sure you're in range of your system, and it will pop up right there. So you would click on it, try and pair with it, and first three would have you put in a pin to make sure you're able to access the specific system. And then as soon as you're paired to the system with your device, you can go into you go into the application, and you'll see this welcome screen that will have the date, time, and the site location. Ours is VW Demo, just for the application. You can swipe down and see that you are connected via Bluetooth. And as you step through, you can see the three main purposes, which would be system configuration, system status, and data information. But in the system configuration, you can set interface, set clock, you have other advanced settings for future reference. And so, for example, you can calibrate the flow rate of the nutrient, and you can set your flow rate. Right now it's reading 40 from my controller, and we want to set it to 50. So we would hit the set button, it would send to my controller via Bluetooth, and bounce back until you yes, your setting is. So you can also see your system, the status of your system, sorry. And you can check your tanks, if it's been tampered with, temperatures, battery life, whether or not the nutrient is used, and you can see these numbers being generated. You can see that they're actually reading what they're supposed to be reading. So the last important piece of this HMI was the data exportation. You would click on the data exportation, export your data, so that you could pull from the data logger on the controller and look at, temperatures over a certain period of time, and use that data for further knowledge to better the crop. And once you've pulled all the data from your microcontroller, you can go into your files on the device, and you'll see we have Bluetooth test data. That was the newer test data. You can pull up the TXT file and either export it later to your computer or for further purposes. This is just giving it the date and times of what was happening at what time. So, and so I will turn it over to John to explain our power.
So providing a suggested power module that will be used. That will be the primary power module to power the system control, moving pump and all the process control modules. So this is a little block diagram, kind of like what it would control. It wasn't until later in the system when we decided that maybe we couldn't find a battery large enough to continuously to hold the charge to power this for as long as we needed it to. So we actually are trying to implement a solar panel and equivalent counter charging system so that we can keep the power module going for 30 days, which was our target. So this is kind of a little list of target performances that Eric sent me. He wanted me to make sure that the power module would fit this target range. And as you can see, we have these little 3 amp, 2 amp, 200 milliamp. This basically means that during these events, this is how much power will be used on the battery. From this, I calculated how many times in a day that the system would go through this sort of, like, how many times the system would turn on irrigation after mode. And with that, I could calculate how big of a battery we needed. And then from there, we had to find a battery that would fit our needs without breaking the bank, overpaying, because we wanted to keep the cost of this whole system to be under about $1,000. We also, for target performance, we also wanted a charge level that would be displayed easy to read. And then of course, because we're environmentally concerned, we wanted the battery chemistry to be environmentally conscious as possible. So this is the battery chemistry. This is the candidates that I went through. Initially, I wanted to research into lithium-ion because this is the battery that I'm most comfortable with. It's the battery that I use on my cell phone, my laptop, and then the battery that goes into electric vehicles. What I found out was that lithium-ion was pretty environmentally friendly, which means it's like highly recyclable and it's easy to recycle that. But it had a high cost for not that many other specifics that were good enough for a system. So I put that aside, and then I decided to look into lead-acid battery. The lead-acid battery chemistry was actually really environmentally friendly. It was low cost. It's been along for a long time, but I think it's been along for that long because it's good enough. It has low maintenance requirements so that no one would have to check up on it to like top the charge or anything. And then it also has like that stuff, low self-discharge current. And then after that, I also looked into nickel cadmium and nickel metal hydride. This is the chemistry that I actually thought would work the best for what we were trying to do. But that was before we decided that we were going to focus on environmental friendly and the cost of the battery. If we were just going to make a power module to power a set of appliance, I think I would try to incorporate nickel cadmium or nickel metal hydride. But as we said before, we're trying to solve an agricultural problem, so I think we're trying to get more people conscious about that stuff. So that's the solution that we have for the power module. This here is a algorithm chart for how to charge a lead-acid battery. I chose a lead-acid battery at 12 volts and 60 amp hours. And then on top of that lead-acid battery, we would place a solar panel and a solar panel controller, which would basically charge the battery to fit this algorithm. But this part of the project is future implementation, and I would like to incorporate and find an actual solar panel that would fit our economy. And next, I'm going to turn over to Zach. He's going to go through sensing technology.
Thanks, John. So before I actually even move on to sensing technology, I'll be talking about the main scope of the sensing technology that I approached. And process control module means a range of temperature measurement, capability to span application scope within the Newton measuring, and also it has to have a high precision local and a high precision remote. And also one of the other things that I looked at was also the cost of the sensing technologies. It didn't have to exceed more than $150. And also the objective was to develop and verify a high precision solution that integrate the process module. So as you can see, the target performance, I looked at the span, resolution, and precision. So I looked at from negative 10 to 100 degrees Celsius, but if needed, we can also move from 0 to 100 degrees Celsius. And resolution was 0.1 degrees Celsius. And precision that we looked at was plus or minus 0.05 degrees Celsius, because it had to have a good precision so that it can actually project all the required data from the temperature sensor. And I've looked into a lot of sensing technologies such as the RTD, the TC, the Thermist, and also silicon-based. But in conclusion, I came into these two sensing technologies because they had the required materials needed for this component of the project. So the RTD has a very high accuracy, and the element sensing span, the area of the elements sensing span is actually higher than the thermocouple. So I actually went with the RTD sensing. And also for the RTD based and processing circuitry, I compared the MAX 31865 as well as the TI Delta Sigma. So after comparing both, I went with the MAX 31865 because it had a higher performance as well as very easy to access. So this has some features that it came with, and it's easy actually to use, and it's fully assembled and tested, and it comes with the USB port. So once you plug into the evaluation kit, and you're dealing with the MAX 31865 software, it projects all the data for the temperature sensor. And also we had to make sure that we didn't have to exceed more than $150 for the project, because we had a certain amount of money for the whole project. And so for the characterization for the RTD sensor, for the evaluation kit, it comes with the hardware and software necessary to evaluate the RTD sensor to digital converter, and also the USB to SPI interface, which can be used to interact with the MAX 21865. As well as the evaluation kit includes the programmable detection of RTD and capable to open and short conditions. So the overall system results, everything was actually successful based on where each part of the group did their own parts. A better version of the HMI, a proof of concept for the controller, the decisions for the power supply module, as well as the RTD transition for the system-wide temperature system. So the future implementations for the group, for the whole project is hopefully have divided into soil columns. Usually what they do in this stage is they grow in plants in different types of columns and have actually sensors within the nutrients. And also 915 megahertz of instrumentation system metering, band transceivers, and also a wider range of Wi-Fi for data file transfer. Also a GSM module for cellular communications, as well as completely integrated solar turbine. And we would like to acknowledge Eric Brooks for actually sponsoring the whole project, and Randy Cohn for working closely with us and helping us to accomplish.
Questions? Thank you.